Let's just take a few minutes to look at enzyme inhibition and sort of refer you to some text content. First of all, we spent a long time thinking about the Michaelis-Menten model and what it means, and you're going to spend some time in the laboratory looking at kinetics data, specifically using a formulation of the Michaelis-Menten model that allows you to make a Lineweaver-Burke plot or a double reciprocal plot. And here I've just written out the inverse of the Michaelis-Menten model, and now we can see that this linearizes the data. You can clearly see that this expression takes the form of y equals mx plus b. Here x, right, is our inverse substrate concentration. And this linearization, while it has its own problems in terms of introducing new sources of error, does make it easy to visualize Km and Kmax. Most importantly, the effects of Km of an inhibitor on Km and Vmax. The intercepts now being 1 over V naught at the maximum, that's the maximum rate, so that's really 1 over Vmax is our intercept right here. And then if we look at the x-intercept, we see then that we're looking at effectively 1 over Km, or negative 1 over Km. So that's the linearization. And I'll say once again that in the laboratory, you should be able to do a nonlinear least squares fit to just the Michaelis-Menten equation itself, but it's a little bit harder to see intuitively what the data mean in terms of, specifically, of inhibition. So, categories of inhibition. Of course, so my cartoons here are just showing you the free enzyme, and then in green we see the substrate bound at the active site. It's easiest then, and in red I'm showing you inhibitors, various inhibitors forms. It's easiest to envision the competitive inhibition in which the inhibitor binds at the active site, competing with the natural substrate for that active site. Uncompetitive inhibition may be a little bit harder to grasp, but basically the inhibitor only binds to the enzyme substrate complex, and perhaps that implies that binding the substrate itself creates a binding site for the inhibitor through some conformational change, perhaps. Finally, non-competitive inhibition comes about when we have an inhibitor that binds to either the ES complex here or to the unbound enzyme. And each of these three has we might think of these as extremes or poles. We might imagine, though, that we have some combinations of some of these. And in fact, I think your book, instead of focusing on non-competitive inhibition proper, it refers to something as mixed inhibition. So I'll stick to the extremes, and then we can talk about the significance of mixed inhibition in class. First, let's look at competitive inhibition. Again, the inhibitor has some binding characteristics that are similar in some way to the natural substrate, and so it competes with the natural substrate for that active site. If we look at the Lineweaver-Burke plot, what I've drawn here is the kinetics data in the absence of any inhibitor, and then here with a little bit of inhibitor added, and then here with a little more added. Now, the idea is that we can easily visualize what's happening with the mechanism of inhibition. So in the case of competitive inhibition, at infinitely high substrate concentrations here at the intercept, the inhibitor is no longer active, right? Vmax is unaltered because ultimately at very high substrate concentrations we can outcompete with the inhibitor for the active site. So we ultimately reach Vmax. The trick, however, is that in order to reach Vmax, we have to go to very much higher substrate concentrations. So the Km is larger, suggesting that in the presence of inhibitor, the binding affinity appears to be lower. And so we can see here that Km gets 1 over Km gets bigger and bigger, Km gets smaller and smaller, smaller as we add more inhibitor. So this kind of kinetic data, these data would indicate the presence of a competitive inhibitor. I just wanted to show you this particular inhibitor. This is a competitive inhibitor of HIV protease. Here is HIV protease. It's a homodimeric protein. It's an aspartic protease, not the kind of protease that we've already discussed, the serine proteases. The active site is composed of aspartic acids, one donated from each monomer. But the active site is symmetric, right? And not only in terms of catalysis, but also in terms of binding. If we look at ritonavir, an excellent inhibitor of HIV protease, and therefore one of the therapies that may be used to treat HIV infection, we see that there's a plane, basically almost a plane of symmetry. This is sort of looking like a peptide backbone, which I think should make sense to you given what the enzyme does. But if we look at the functional groups that might be determining binding affinity, we see that we got this symmetric pair of phenyl rings. We have this thiazole rings out here like this. And so you can easily see in gross terms that how an inhibitor, a competitive inhibitor, must not only reflect the substrate, the natural substrate, but it also has to have some reflect in some way the binding determinants on the protein itself. But back to inhibition, now let's turn to uncompetitive inhibition. In this case, the inhibitor binds only the enzyme-substrate complex, forming what we call an inactive enzyme-substrate inhibitor complex. This is an interesting case because since the enzyme-substrate inhibitor complex is not competent to carry forward the chemistry, the Vmax is lowered. So 1 over V naught at the intercept gets higher and higher and higher. On the other hand, Km appears to be smaller. That is to say, affinity seems to be greater for the substrate in the presence of the inhibitor, and that's only because the formation of this enzyme-substrate inhibitor complex pushes the equilibrium towards the bound state. So increases the apparent affinity even though chemistry is not taking place. So we see this parallel set of lines showing us that 1 over Km gets larger and thus Km gets smaller. Finally, non-competitive. This again is maybe the extreme version here, whereas your book might describe more of a mixed inhibition, that is some combination of non-competitive and uncompetitive. In this case, we're binding to either the ES complex, note the green substrate there, or to the free or unbound protein. Probably at a site that's distant from the active site, more or less. The enzyme's Vmax is lowered. Inhibitor binding interferes with the chemistry, so we see that Vmax is impaired. And again, I'll refer back to uncompetitive inhibition to think about how binding to the enzyme substrate complex could affect that. But Km is unaltered in this extreme version since the inhibitor impacts chemistry, but not the affinity for the substrate. Now, I guess I should say that we'll think of this as an extreme example because perhaps it might be difficult to envision a physical system where this could really be the case. In fact, we might imagine that binding to the just as binding the natural substrate at the active site often alters the structure of the protein, maybe even creating the presence of a binding site for some other ligand or inhibitor, so too the binding of the inhibitor may alter the structure of the protein, which could affect the affinity for the substrate of the protein for its substrate. So that's why the book focuses on a mixed inhibition model, but it's useful to think about these extremes, and then that helps us think about the more realistic and complicated systems.